Hi, I'm Mike Morrow. I'm the president of the St. John Center of the RASC. And welcome everybody, and welcome. We have some visitors, and welcome visitors, welcome members. I'm going to start with an acknowledgement. We acknowledge that the lands on which members of the St. John's Center of the RASC live and pursue our hobby are situated in the traditional territories of diverse Indigenous groups, and we acknowledge with respect the diverse histories and cultures of the Beothuk, Mi'kmaq, Innu, and Inuit of the province. And so I'm going to start by inviting Randy to come down. We've got a sad announcement to start with, and so I'm going to have Randy come down and say a few words, and that's because an old friend of ours just passed away. So
thank you. Yeah, I got a call this afternoon from Samantha, his daughter, saying that Fred had passed away within the past week. Obituary should appear tomorrow. Services on the weekend. I invite you to find out and attend if you're able. Fred was a member for 38 years, on the executive for more than 20, president, etc. Long-term librarian. What can I say about Fred? He got the RASC Service Award in 2012, and he was the coordinator of the 1994 RASC GA that we had, and a key member of the organizing committee for the second one in 2004. Fred spent 40 years teaching at MUN and retired in 2011. He got numerous awards, well noted for his science teaching, well known also in the science fair circles.
yeah, I was just going to say,
organizing local ones, and also the Canada-wide Science Fair. One of the most productive ones was held here. Fred helped co-author a manual for people organizing and running science fairs, which is quite popular and well received. I guess I'm not going to take up all the time, but we'll talk more about Fred next month in our 60th anniversary party and stuff, and we'll prepare and send out a memorial note on him. So I know a lot of you know Fred, and if you didn't know, we use the picture from Signal Hill called the Comet Watch. A bunch of us on the side of Signal Hill. That was taken by his daughter, Sam. Okay.
thank you very much, Randy. Certainly a sad event for all of us. I knew Fred through teaching rather than not as much through the astronomical, through this group, but of course he was still involved. I still saw him online from time to time, even the last few meetings. So certainly an important part of our past.
He also taught physics, I think.
He taught science. Yeah. And so welcome visitors. These meetings are open, but if you are interested in membership, we do provide the supportive community, help you learn about astronomy. One of the benefits is we have a chat group, RASC Talk, where people share information, and there's a lot of mentorship there. There are some publications. We have low-cost equipment rental, and Gary puts on, couldn't find you because I was looking for the beer. Gary puts on planetarium shows for us periodically, so it's easy to join. There are some bulletins, weekly and monthly, that people get. So a couple announcements. Our next meeting is January 21st. And it's going to be the 60th anniversary of the center. So there'll be some, some programming related to that, and maybe even some treats. And Ezekiel has been learning about false color imaging. And so he's going to tell us what he learned about, give us a short talk about that in January. So we're looking forward to that. Thank you, Ezekiel. And, oh, Randy, there was something about the Stellarium course. They've changed something?
There were several centers in the Maritimes that were organizing this course. And it's come back that they can't do the January date proposed. So they're going to come up with a new date, possibly March.
Okay, so what Randy was saying was for the Stellarium level 1, it's not going to happen in January. It might be in March, but we'll, when we hear, we'll pass that along. Okay, thank you. And so with, and calendars. Are calendars done?
A few RASC calendars. And we have another shipment of the local ones coming in, but they're delayed in shipment somewhere.
Okay, so there's still a few of the national calendars, and we're expecting more of the local calendars. You can get in touch with Randy. You can pay $20 by e-transfer to our payments address. And I've got this is probably the last time I'll run this this reminder that membership renewal, it used to be that there was a grace period, but now they just warn you a couple times before your membership runs out. And then if your membership runs out, you have to go through restarting it. Okay, and we have the AstroImaging contest going on. It's pretty much the same as last year. We'll start accepting submissions to I think it's photos at stjohnsrasc.ca. I think it's, yeah, there it is there. And they're basically images captured between the end of the contest last spring and the end of the submission deadline, which is March 31st. The categories are solar system, deep sky, landscape, and sketching. And there's some other details here. This is also up on the website, and we'll do the judging the same way. People will basically vote. We'll have a site that's set up. The voting will be to view them. The voting will be an online poll, and there'll be various awards. We have some sponsorship Jim Johnson is setting up. Probably be at least what we had last year. But this year, we're also, in addition to best overall, we're going to look to do an award for the best submission from a first-time entrant. So that's something to look forward to. So with no further ado, well, actually, there's going to be lots of ado because we have to disconnect one computer and connect up the other one and see if everything works. But when that's all done, I'm very pleased that joining us again for our December meeting is Dr. Anna O'Grady, who's at the McWilliams Center for Cosmology and Astrophysics at Carnegie Mellon. And she's going to talk about a buddy for Betelgeuse. And so I'm going to stop sharing and unplug and get Anna share. And then I'm going to mute myself.
Okay.
Good.
Okay. Awesome. Okay. Apologies for that. Sometimes Macs don't play well with others, but we are good to go. Okay. So I'd like to thank Mike and the center again for the opportunity to speak to you. As I have said previously, and is still the case, this is my favorite place to give a talk. So I love doing this as a way to cap off my year. Last year, I mostly talked to you about the yellow supergiant binary project that I've been working on, but I also gave you sort of a quick fire introduction to a project that had very rapidly fallen into my lap at the end quarter of 2024, which is finding the buddy who you are seeing occasionally fling around the screen here. There he is, to Betelgeuse, the nearest red supergiant to Earth. And in the years since then, this project has gone through many different twists and turns, and I have sort of
Just a second, Anna.
Yep.
Still not hearing.
I can hear her online, but not. I can hear her online, but not in the room very well.
Oh, okay.
Maybe just speak up.
Yeah, okay. And I'll,
Either that, yeah.
okay, yeah. Okay. Yeah, yeah. And I'll make sure I'll stay close to the laptop as well so that people online can hear me through the microphone. So I will be giving you, at least from my perspective, what the final word is on this project to a sense. So, okay, great. So Betelgeuse, seen here, the right shoulder of Orion, the Hunter constellation. This is the closest red supergiant to Earth and is the 10th brightest star in our sky. And because of both of those things, it attracts a lot of attention. Right? It attracts a lot of attention. There have been a lot of eyes, amateur, professional, and everything in between on it over the years. And as the closest red supergiant to Earth, there are lots of questions and studies on its various properties and trying to really understand what makes this star tick, what's going on with it, etc. So one of the things, one of the sort of main properties of Betelgeuse is that it is a variable star. If you have a dimmer switch in your house and you can turn it up and down and up and down and the light goes up and down, that's kind of what a variable star does. Its brightness changes over time. But the cosmic dimmer switch for these stars is something called stellar pulsation, where quite literally the star is getting bigger and smaller and bigger and smaller. As it gets bigger, it's expanding, and that expansion causes the outer layers of the star to cool down. As it cools, it gets redder, and then it goes back in. It starts to contract, the gas heats up, it gets hotter, brighter, and yellower in this case here. So this is showing you a very extreme example. Betelgeuse doesn't change its color from red to yellow. It just goes from a very dark red to a slightly dark red. But this is showing you sort of what we think the actual physical mechanism for stellar pulsation is. The star is literally doing this. It's moving back and forth and back and forth. And you can look at this in a sort of graphical way through something called a light curve. So this here is a light curve. On the horizontal axis is the magnitude in V, or visual. So this is sort of a proxy for how bright is it to our human eyes. And then on the horizontal axis here, the overall scale is arbitrary, but the number is days. So each blue point is an observation of how bright Betelgeuse was on a given day. And as you can see, just looking at the blue in this image here, it goes up and down and up and down and up and down and up and down, and it's doing this for a long time. It goes a whole lot down right here. This is 2022. This was the Great Dimming. Some of you may remember this as the time that Betelgeuse got really, really dim. People freaked out, thought it was going to explode. It wasn't going to explode. It burped a bit of dust, basically. But this is our light curve of Betelgeuse going back nearly 100 years, so a wealth of data. So you can see, if you just look at the blue, you can see the sort of general up, down, up, down, up, down idea there. And if you were to count the number of days from one peak all the way down to its dimmest point and then back up to its brightest point again, that would be the pulsational period, where the period is the number of days it takes to go through one variability cycle. So looking at the blue here, you have these primary periods of about 400 days. It takes Betelgeuse about 400 days to go from really big, contracting down, and then going back out again. Lots of stars do this. We think we have a handle on how this pulsation works relatively well. But as you can also see, guided by the very obvious red line going through this diagram, if you sort of take a step back and you don't look at the small scale structure, but you look at the general shape of this light curve overall, you can kind of see this overall down and up and a little bit here, but up and down and up and down and up again over a much, much, much longer period than those little 400-day guys, the tops of the blues. This is something known as a long secondary period. In Betelgeuse, it is 6 years long, a little over 2,000 days. Compare that to the 400-day normal period. And these long secondary periods, they happen in about a third of all cool, large red stars like Betelgeuse, these red giants, red supergiants. But for a very long time, there has been vigorous debate on what is actually causing these to happen. Is it another form of pulsation? Like the star is still pulsating, but it has sort of like an upper harmonic to that pulsation very slowly over time. Is it a dust mechanism? Is it something else going on? People have debated this for a really, really long time. And in August of 2024, a certain paper came out from now a collaborator of mine, Jared Goldberg, titled A Buddy for Betelgeuse, Binarity as the Origin of the Long Secondary Period in Alpha Orionis, where Alpha Orionis is Betelgeuse. So essentially, Jared Goldberg and his collaborators, they are theoretical astrophysicists, and they used a wealth of data, many, many decades of data, spanning many, many different types of observations. And they exhaustively went through every single hypothesis that has ever been suggested, ever, for what might cause a long secondary period. There's lots of things on here. I understand some of them. Jared and co went through each and every one of these and exhaustively, using all of the data that they had compiled, ruled out every single one except binarity, dust modulation, which I'll explain what that is in a moment, but essentially saying the only hypothesis for which all of the evidence, all of the observational data we have matches together, the only one that has check marks all across the way, is binarity. So Betelgeuse has to have a companion with it, another stellar object, and dust modulation, which I'll explain what that is in a moment. So this is this, I love this plot, I use it in every talk. This is a schematic that Jared made for his paper, and I love these types of diagrams. So on the top here, this is the same light curve that I was showing you before, except they've all been sort of, if you took the light curve and you put creases in it at the period of the long secondary period. So every 2,000 days, you put in a crease and put in a crease, and then you fold it on top of each other. This is the shape that you would get. So you just see the one big long curve from the long secondary period. This is the light curve up here. So this is showing you how the brightness of Betelgeuse changes over the long secondary period. Down here is something called the radial velocity curve. What this is how is the speed of the surface of Betelgeuse changing? If you think of the pulsation of Betelgeuse, the surface is going in and out and in and out. From an observer, if y'all are telescopes, the surface at the speed is changing. It speeds up, it gets quite fast, and then it slows as it gets to its maximal point, and then it turns around and starts to fall back, and it speeds up again. They saw that essentially there was a speed differential, so they were seeing a change in Betelgeuse's speed along with how bright it was, but due to some very interesting mathematics that I'd be happy to explain to people later, essentially mathematically, the only option to explain the shape of the speed curve and the shape of the light curve was that Betelgeuse is being pulled around in an orbit with a companion object. Jared coined the term Beetle Buddy, which is what I'll be using for the rest of the talk. So Beetle Buddy is this little dark circle here, and it and Betelgeuse are in an orbit with one another. They are swinging around each other. And essentially what's happening, Betelgeuse as a red supergiant, it's very, very dusty. It has a wind that is taking material off the surface of the red supergiant, and it's sort of leaving it all around as this dusty cloud around itself. But Beetle Buddy, whatever it is essentially clearing out a little pocket in that dust. It's moving around in the dust cloud, and it's able to kind of irradiate away a little pocket in the dust, such that when Beetle Buddy is in front of Betelgeuse, there's less dust in the way. So both the light from Beetle Buddy and the light and more light from Betelgeuse is able to break through and get to the observer. This is why the light curve is at the highest point at this part of the schematic. And then if you think about two stars orbiting one another, again, if you guys are the telescopes and you're measuring the speed, if two objects are orbiting around each other and say you're looking at Betelgeuse, which is my fist, and Beetle Buddy is my pinky. As they're moving around each other, at this point in the orbit, if you're looking at the velocity going in and out, when they're either right behind each other or right in front of each other, Betelgeuse isn't moving in this direction, right? It has no motion, like relative to my face. But at the side points, Betelgeuse is moving towards you, and as it comes back around, it's moving away from you. So that's where you see it's at these points when they are, from our perspective, right next to each other on the sky. That's when the highest and lowest points of the RV curve come in. So a lot of complexity went into figuring this out from Jared. So this was really, really interesting. And one of the cool things that they got from this is that they're essentially able to predict going forward in the future at what dates these phases would be occurring in the future. And keeping in mind, I was reading this paper when it came out August, like late August, like August 30th or something, 2024. And the date of the next RV minimum is December 6th, 2024. When is the radial velocity at a minimum? Here. So that corresponds to this cartoon right here, when Betelgeuse and Beetle Buddy are apart from one another. Betelgeuse isn't in front of, Beetle Buddy isn't in front of Betelgeuse. It's not hiding behind it. They are separated from each other on the sky. Or in other words, this is one of only two configurations where you could possibly see them as separate objects. The other one, which would be RV Max, that wouldn't be coming until November 2027. So I thought that this was pretty interesting. And I got chatting with my collaborators at Carnegie Mellon. I reached out to Jared and his collaborators, and we started to ask the question, okay, but how can we see it? There's a little bit of a problem in that Betelgeuse is a red supergiant. Its luminosity, if you compared it to the sun, if the sun was one light bulb, whatever wattage, just a light bulb, Betelgeuse is almost 100,000 light bulbs. So if you had 100,000 light bulbs together, and then a little bit away from it, there's one light bulb. Say in New York, some baseball field in New York, you've got this set up. And then you're in Chicago, and you're trying to see, okay, can I see the one little light bulb next to this huge field? You're not going to see it. It is way, Betelgeuse is way too bright to just conventionally look for, we think we're seeing the presence of it in how this light curve is changing, but we want some more distinctive identity. We want to be able to look at some sort of quality and say, this is definitely coming from the companion and not from Betelgeuse. Okay, so the first question to ask is, how do we best see it? We have lots of options available to us in astronomy. There's lots of ways to do astronomical observations. What would be the best tool, the best method to try to basically get a good picture, essentially, of that? So Beetle Buddy is what exactly? Well, we know from Jared's paper, and then also a totally independent paper that came out around the similar time, that in terms of the mass, or how heavy Beetle Buddy is, it's somewhere between half the mass of our sun to 2 times the mass of our sun. But probably, if you sort of take the average of these measurements and what's likely, it's probably about the size of our sun. So you could, for the moment, think about the system literally as the big red supergiant and then our sun orbiting around it, which is pretty interesting. Okay, so we know that this is the mass of Beetle Buddy. However, normal stars like our sun are not the only kind of objects that exist in the universe at this scale. There are other objects as well, and particularly objects that fall into this mass range. And when we thought about it, there were 2 options that made sense astrophysically for what Beetle Buddy could be: a neutron star or a regular star. Where a neutron star, if you're not familiar, these are the dense cores left behind when a massive star explodes as a supernova. The really big massive stars will create black holes when they die. But the stars that are still big enough to explode as supernova, but sort of on the low end of that mass range, they will make neutron stars, which are essentially what it says on the tin, these dense balls of neutron material that are incredibly dense and incredibly heavy. And neutron stars exist in a mass range between about 0.8 to 1.5 times the mass of our sun. So it could be a neutron star by the mass that we know it to be, or it could be a regular star. And when I say a regular star, I literally mean like our sun, just totally normal. Okay, so I'm going to walk you through both of these options. Myself and are born in a binary, and one that will become Betelgeuse is actually the smaller of the pair initially. Its partner is a bit bigger than it. Maybe Betelgeuse is about 16 or 17 times the mass of our sun. So maybe its partner is 18 or 19 or 20 times the mass of our sun. And the reason that this is important is that larger stars burn through their fuel faster, they live out their lives faster, and they will explode first when you have two stars that are born at the same time. So in this scenario here, the bigger star eventually goes boom as a supernova explosion and leaves behind a little neutron star. And then this is the configuration we have today, a neutron star in orbit around Betelgeuse, our slightly smaller red supergiant in this scenario. So, okay, we think it's a neutron star. Despite the name, neutron stars don't shine in the way that normal stars do. They don't have nuclear reactions going on in them. So how does one see a neutron star? You don't see it exactly. However, remember how I mentioned earlier that Betelgeuse has a lot of dust around it and that Beetle Buddy is sort of careening through all of this dust. Well, neutron stars, due to their intense gravitational pull, they pull that dust onto themselves, and because of the intense gravity at their surfaces, they undergo a process called accretion, which is a fancy way of saying that the neutron star sort of gobbles up the material, but in a really energetic way. And you get something called an accretion disk. And accretion disks, when they occur, are extremely energetic, so energetic that the energy that they produce comes out as X-rays, not as normal light that we can see, not even as ultraviolet radiation. They come out as X-ray radiation. So if Beetle Buddy is a neutron star, it's moving through all this dusty material around Betelgeuse. It should be gobbling it all up, and it should be producing an accretion disk and like a lighthouse just beaming X-rays out into the universe as it does so. So one of our their first project is that we politely asked the Chandra Space Telescope, which is an X-ray imaging telescope, to look in the general vicinity of Betelgeuse at the date around December 6th, when the two were supposed to be really far apart from each other, and say, do we see any X-rays? And again, from the neutron star hypothesis, and with the amount of time, how long we asked Chandra to look in that location, if it's a neutron star, we are going to see it, period. So this is the image that Chandra produced for us after a very long time. Does anyone want to guess where in this image is the Betelgeuse Beetle Buddy system?
Lower left, sir?
Lower left?
Yeah. Right there.
Like this?
Yeah.
Okay. Right in the middle? Some people remember from last year. So this is the location of the system. These guys here are background galaxies. These points here are other galaxies far, far away from our own that have black holes at their center that are kind of doing what a neutron star does, just on a much bigger scale of gobbling up all the material around them and very loudly telling the universe that it's doing this through X-ray emission. This, yeah, right here is where Betelgeuse and Beetle Buddy are. There is nothing there. So Beetle Buddy is definitely not a neutron star. Negative results are a little sad, of course. It would have been really, really cool to discover the closest neutron star to Earth. But this is still important because it very, very conclusively rules out this avenue. It can't be a neutron star, so it's a normal star. So rolling back the clock a little bit, Betelgeuse is a red supergiant. It's kind of an elderly star. It's in the last phases of its life. When it was a young star at 17 solar masses, that's very, very big, it would be on the main sequence a very hot O-type star. Very hot, very, very blue. So you have something like this on the main sequence where you have, you know, a sun-like star around 1 solar mass, and then this like 16 solar mass main sequence star. And then time moves on, and then you get to today, where it's a red supergiant and a main sequence star, right? The issue, and this is one of the fun parts of the project because I rarely get to think about this and the other work that I do, is age. Betelgeuse is about 10 million years old. We know this for other reasons that people have put a lot of work into understanding, but we're pretty confident, you know, maybe 2 or 3 million years off, but it's about 10 million years old. And winding the clock back to when these stars were on the main sequence is actually not enough, because stars don't just pop into existence out of nowhere. They form by big clouds of dust and gas collapsing. And it takes time for clouds to condense down into stars, and eventually the density gets high enough in the middle that nuclear fusion ignites, and then you have a star on your hands. And just like how massive stars go through their lives more quickly, the big dust clouds collapse more quickly than the little dust clouds. So the big cloud that made Betelgeuse got to make Betelgeuse faster than the little cloud that makes Beetle Buddy. And how much faster exactly? So you have a really, really big cloud. It starts to condense. You get a protoplanetary disk and a protostar, and then you get a 16 solar mass main sequence star, and it grows up to be the Betelgeuse we know and love today. This whole process from dust cloud to being on the main sequence, this takes about 10,000 years. It's super quick for massive stars like Betelgeuse. Okay, what about for Beetle Buddy? And this is assuming that the dust clouds start to collapse down at the same time. So you have a littler dust cloud, you know, it forms its protoplanetary disk, and then it produces a 1 solar mass star, just like our sun. Who wants to guess how long this takes? Millions? Okay. This process for a 1 solar mass star takes 100 million years. Today, we're at 10 million for Betelgeuse, and 10 million is not 100 million. So Beetle Buddy is not here. It's still here. It's not a star yet. It hasn't begun nuclear fusion. So Beetle Buddy is a pre-main sequence star. It is a protostar, like these beautiful ones that the ALMA telescope takes images of. You have these slowly forming sort of core in the middle that will eventually ignite hydrogen, but not yet. And you have this protoplanetary disk around it, right? So consider our solar system. We have our sun and our planets, but we don't have all this stuff around us, right? There isn't just sort of dust and gas left over. It's pretty clean, all things considered, except maybe the asteroid belt. You know, you have the Kuiper belt further out, but you don't have all this stuff in there. And the reason for that is that once the star turns on, once it ignites nuclear fusion and starts to shine, that light, that energy literally evaporates anything that's left that hasn't basically battened down into a big enough ball planet to survive that. So that's why planetary systems like our solar system don't just have all this junk lying around. So consider the configuration of our system. You have a very big cloud and a littler cloud. This one evolves more quickly, and you get this hot, very, very hot blue main sequence star and a protoplanetary disk, a protostar that's still forming. The winds from OB stars are immense. They are extremely powerful, and we know how close these systems are today from the work that Jared and them did. So probably what's after happening is that Betelgeuse was quite rude to its neighbor and blew its disk away. So what you have left is essentially the core of the protostar, but no disk left. And then eventually you get to today, where you have the red supergiant. So it is a pre-main sequence star without a disk. This has lots of interesting implications. I can chat about those later, but it basically had consequences for how we went about the search, because the nice thing about these protoplanetary disks is that they give off lots of nice signatures. They're kind of easy to find in certain ways, but that's not what we get. So how do we actually find this? Traditionally, what you might want to do for something like that is use stellar spectroscopy, where you're taking the light from a star and spreading it out into all of its colors and looking for lines of hydrogen or helium or something like that. You know, Betelgeuse would have a spectrum. This is a dwarf star, but quite red spectrum, something like this. You're looking for a protostar, maybe you'd be able to find something different. One thing that is working in our favor is the fact that this is in a binary system. This GIF here is showing an example of a star and a planet, but Betelgeuse compared to Beetle Buddy, similar size. Just pretend that this is a, you know, a diskless protostar, and you're good. As these systems move around each other, there is physical motion happening. So the light that is coming from these stars is getting stretched and compressed because it's a wave. You have a Doppler shift happening as the stars orbit around each other. And that has an impact on the spectroscopy. This is a GIF from a colleague of mine at the University of Toronto that I think is absolutely excellent. So on the left here, you can imagine that the yellow dot is Betelgeuse and the smaller blue dot is Beetle Buddy. You can see it goes behind, and then it comes back around and it's in front. This is what the system appears to do to our eyes. It's quite edge-on like this. And if you're looking for absorption lines, quite literally, the lines, and this would be from the yellow star in this one, but they shift back and forth relative to each other if there's this motion. Okay, so then in the system that we're looking at the dates we're looking at, what's the configuration of the system? At what speed are these stars moving? Well, luckily for us, at the time that we're looking at it, when they're separated from one another, so Betelgeuse is coming towards us and Beetle Buddy is moving away. Betelgeuse is moving towards us at about 2 or 3 kilometers per second. It's very large, it's slow. Beetle Buddy is racing along its orbital track at 46 kilometers per second. So if you think of the difference in speed between these two objects, there's a difference in speed of about 50 kilometers per second. That's a lot. So any elemental line, say you were looking for a hydrogen line from Betelgeuse and the same hydrogen line in Beetle Buddy, there will be a 50 kilometer per second difference, which becomes a difference in the wavelength because of how light shifts as a wave at this moment in time, essentially, because of the configuration of the system. And that is exactly what we decided to look for. So this is a plot showing wavelength just versus overall intensity. The yellow line here is an old observation of Betelgeuse, and I'm focusing in here on a hydrogen emission line. So this is a species of hydrogen that's emitting from Betelgeuse, and in particular, we're at very short wavelengths here. We're out in the ultraviolet, and these green lines here, these are models of pre-main sequence stars. So exactly what Beetle Buddy should look like. And you can see that the center of the orange and the center of these green ones have been shifted by about 50 kilometers per second, because that's how we expect the radial velocity to imprint itself on the spectroscopy. And then as a consequence, you get what we think the difference should be is this sort of tiny little mess of green lines here. Essentially, the difference between these green lines and the orange line, that's what we're trying to look for. Very difficult. Easier if Beetle Buddy is larger, if it's a bigger star, if it's bigger than 1 solar mass. And this is just showing you another example of a different hydrogen line, but the same idea. The line from the protostar is shifted, so the effect that it has is visible, even though it's much less luminous than Beetle Buddy, or sorry, than Betelgeuse. Okay, so as I mentioned, we're doing this in the ultraviolet, so we need to go to space for that. So we politely asked the Hubble Space Telescope to look at this for us. It was successful, and then I got to do something that was really cool, which was wake up at 3:30 a.m. in Pittsburgh to take a picture of Betelgeuse at the exact same time that Hubble was taking a picture of Betelgeuse, which I thought was pretty cool, and very worth it. Even though I had to work the next day, it was okay. Okay, so we get the data down from Hubble. What do we see? Now, what I'm showing you, this is very similar to the plot that I showed you before, except The black line is the old Betelgeuse that we had. In particular, the black line was taken when Beetle Buddy was behind Betelgeuse. So there should be no light from Beetle Buddy. It makes it a good template. And the pink and the green, sorry, the pink and the blue we had 2 observations on Hubble. Those are our observations. So if Beetle Buddy is of similar mass to any of these green lines here, we should see the pink and the blue pop up to like here or like here. And we don't see that. So what does this mean? So we're able to very conclusively say that Beetle Buddy is not this green line. This green line is this is a 2 solar mass protostar. You remember the total allowed mass range went from 0.5 to 2. We can really, really conclusively rule out it can't be that big. For the 1.5 solar mass stars, it's marginal, but they could be hidden in here. Essentially, the data that we have isn't quite good enough to rule that out. So that's tricky. So we do all of this. Our papers are published in like the spring. We're like, okay, we can't rule a whole lot of stuff out, but we ruled out a neutron star. We ruled out a big protostar. You know, we're curious, is anyone else going to do anything, or are we going to have to wait until 2027 when it comes back around from behind Betelgeuse? And then a new challenger approaches. In July of this year, 2025, this paper goes live on the archive, the probable direct imaging detection of the stellar companion to Betelgeuse. Important note, almost every single person on this author list is an expert in observing exoplanets. So looking for planets around other stars, or more simply, looking for really small things around other stars. And that gives them a little bit of an edge in looking for Betelgeuse. They used a telescope in Hawaii, so they weren't in space, they were on the ground, and they did something called speckle interferometry. And speckle interferometry is really, really cool. And I'll briefly explain what it is. If you are looking at the night sky and you are on Earth, so the atmosphere is in your way, you get all these atmospheric fluctuations, light bends in certain ways, and you get sort of a little bit of a mess. What speckle imaging does is instead of staring at an object for a really, really long time, say 2 hours, and just collecting all of that light, and you build up the sort of interference from all those little weird fluctuations from the atmosphere, you instead take a whole lot of really short images. You're maybe taking 10-second images, but you take 10-second images constantly for 2 hours. What that's going to do is every single fluctuation is transient in time. It isn't steady. It's going to move around because the atmosphere is moving around. Whereas the actual object that you want to look at, that's not moving. It's an object out in space. It's not moving on a 10-second or even 2-hour time frame. So if you put all those images together and you get rid of anything that changes between the images, you get rid of all of the interference from the atmosphere, and you are only left with the things that don't change, which is your astronomical object. This has been used to great effect to find exoplanets. This is an example of an exoplanet that was found around a star, and you can sort of see in the GIF here how it's moving around a little bit because there's still some fluctuation, but it's able to find this, and this image is not just full of atmospheric aberrations. So during the Great Dimming in 2020, everyone everywhere pointed every telescope at Betelgeuse, including this one. So they had a speckle interferometric image of Betelgeuse during the Great Dimming. And to great coincidence, thankfully, during the Great Dimming, the orbit of the system was such that Beetle Buddy was behind Betelgeuse. So you should not see it. It's behind it. It's completely blocked because Betelgeuse is way bigger. So they have this as sort of a template image. This is what it looks like when Beetle Buddy is hiding. And then they went back on December 9th of 2024, and they took another image using this speckle interferometer. And what is that? It's very subtle. This color bar here is essentially just in marks of intensity. How intense is the signal? The big red dot at the middle is Betelgeuse. So like we are very sure that Betelgeuse is there. But you can see there's this sort of cyan color that is not there in this image. When you do speckle interferometry like this, you get ghosting, which is what this thing on the side is on the other side. The thing that the big yellow arrow is pointing to is the true signal. So it's a weak signal, but it is exactly where Beetle Buddy should be. We have an idea of the orientation of the system. So the fact that it appeared right here and not here or here or here, but that it appeared right here is a really good sort of tip on the scale for this actually being real light coming from the companion. And here is the very pretty image that they did for their press release. So we have Betelgeuse and this faint light coming from the companion. They estimated, it's very difficult to do this, but they estimate that it's about a solar mass, which is not inconsistent with our work because we weren't able to rule out those lower masses. And yeah, they believe that they have actually seen it using the techniques used for exoplanet imaging. Little disappointed that we didn't see it first, but this is still very, very cool. And yeah, an interesting conclusion to the story. So very broadly, we conclusively ruled out that Beetle Buddy cannot be a neutron star, and it's probably really small, around the size of our sun, except it's not like our sun. It does have to be a protostar just based on the timeline of the system and how old Betelgeuse is. So that brings us to the end of the science. When this one came out in July of this year, I thought, okay, this is it now, you know. In 2027, when it swings back around, everyone's going to look at it again. But there is one last thing that I just briefly want to talk about as a little bit of a plug, and I promise you this is going somewhere. Some of you might be familiar with Celestial Buddies. This is the company that makes these really cute, like they made the whole solar system, that's the sun, you know, all these very, very cute things. I have one. I have the binary star system. This is Polaris A and B. And one day after all this come out, I was very much procrastinating and just looking at them on my desk. And an idea came into my head, and on a total whim, I emailed Celestial Buddies and said, hi, this is who I am. I worked on this Beetle Buddy project. You might think it's cool, like whatever. I didn't expect to get an email back. One thing led to another. And myself and Jared are official contributors to the Celestial Buddies Beetle Buddy Discovery Pack, which is 2 stickers and an informational booklet. This is live. You can buy it from Celestial Buddies right now, which is super delightful. And I love it when it's a story like this that can sort of go into the public interest like this. And super, super secretly, this wasn't initially possible due to supply chain issues, but now that's been resolved. So I have been told that hopefully not too long in the future, there will be a plushie of the Betelgeuse Beetle Buddy system. So thank you for indulging me on that note. And that is the end of the talk. So thank you.
I'm sure Ann would be happy to answer some questions. Okay, Jim first and then Nikolai.
Is Jupiter a protostar?
That is a great question. So it is not, because to be a protostar, you need to have enough mass to eventually ignite hydrogen in your core. And Jupiter is not quite that big. Jupiter is like slightly smaller than what we would call a brown dwarf, which would be a type of star that can get to a little bit of hydrogen burning, but not full nuclear fusion. So yeah, if all of the rest of the mass in the solar system, and then maybe like you shaved a little bit off the sun, if all of that had gone into Jupiter, then maybe in that case, our system would be a binary star system of our sun and Jupiter. But in that case, we wouldn't exist. So
The reason I asked was that one thing I learned in the Rocks and Stars course was the fact that Jupiter actually radiates more energy than it absorbs.
Mhm.
from the sun, so. So it's, you know, they made the point that it's had some properties of a massive gas that just couldn't get it together.
Yeah, exactly. There is a very smooth spectrum from things that are as big as Betelgeuse down to our sun, and then down to gas giants like Jupiter. It is a very smooth spectrum, and just at some point you are big enough that you can get nuclear fusion and you start to shine. But yeah, that is absolutely a spectrum, and Jupiter is on it, just not quite big enough to accept in 2001, where it does actually become a star.
Nikolai?
Amazing. Pardon.
Thank you.
I have two questions. The first one is, if you're a protostar, just trying to grow with your disk around, 100 million years, then all of a sudden a mean neighbor comes around and blows away that dust, and I assume it halts the growth. What happens to that protostar? Does it just stay like that forever? Or does it move in certain direction in its growth?
That is a great question. So I do not know exactly. This is something that I think we're sort of acknowledging the fact that binarity is so important. There's many, many binary stars in the universe, and this sort of scenario might happen. It's sort of a newer thought process. My gut instinct is that you would essentially end up with a brown dwarf. When you have a protoplanetary disk, the star is growing, it's still taking on gas, it's growing and growing, and it's growing at the same time that it's condensing and getting denser. If you get rid of the disk, it will still continue to collapse. So I think it's really dependent on how big the core was at the time that the disk gets blown away. There's a chance that it is a brown dwarf, so it doesn't ignite nuclear fusion, it just does some light like deuterium burning. If it's really big enough, then maybe it would become still a star, but just maybe it was, if nothing had happened, it would have been like a 1 solar mass star, but now it's only going to be a 0.7 solar mass star. But I don't know exactly. This is sort of a new sort of avenue. But yeah, excellent question.
Two questions. First, easy one. How far is the dwarf star from Betelgeuse? Second one, there's a very large telescope they're building down in South America, big giant one. You think you'll be able to get better imaging with that?
Yes. So Beetle Buddy, not to scale in this, it is, if you take the radius of Betelgeuse, so how big it is from core to edge, and then you go 1, 2, and a little bit more, that's where it is. So it's about 2.2 times the radius of Betelgeuse away, which is very, very close. That's why you're able to determine that from the light curve, from the radial velocity curve. That's why we know it has to be plowing through the dust around Betelgeuse, because that's very, very close. And then, yes, the Large Magellan Telescope. Yes, larger mirrors, bigger aperture would definitely be able to help. If you're viewing it from the ground, the light differential, how bright Betelgeuse is compared to how dim Beetle Buddy is, I think you would still need to do speckle imaging. So you'd want to make sure that that telescope has a speckle imager on it. I feel like it will, because it's one of the next big ones. But yeah, I don't know if GMT will be up in 2027 when Beetle Buddy comes back around the side, but if it's close, then yes, that will be one of the many telescopes that will be pointing right at it.
Any other questions? Randy, are there any questions online?
Yes, Richard Newman here.
Okay, well, let's thank Anna again. That was a wonderful talk.
Oh, God.
Wonderfully clear. We have
Richard Newman was speaking here.
no.
Oh,
Richard, will you say that?
Hello?
oh, wait. Yes, go ahead. Sorry.
Okay, I was just wondering if Beetle Buddy was, its rotation right now is on plane with Earth.
Yep.
If it was 90 degrees off and going around the other, would we notice anything at all?
That is a great question. So essentially, if instead of it going around How it currently is like this, you meaning if it was face on and sort of going, I don't know if you can see me, but like going face on like this.
Correct.
Yes, thank you. So we would not have been able to see from the radial velocity or light curve of Betelgeuse because all of the motion of the two would be happening in that planar direction. Towards Earth, nothing is going on. Now, it would make it much easier to do the type of direct imaging that the Howell team did, because then all the time you see it. It's separated from Betelgeuse. It's never hiding behind Betelgeuse or in front of and impossible to see. So, you know, it would be easier to image in that sense, but the way that we knew it was there in the first place was because of how it altered the motion of Betelgeuse. And that would not have been able to be seen if it was plain on. So would we have been going and doing speckle imaging of Betelgeuse if we hadn't thought, oh, hey, there might be a binary star around this? So I think probably not in that case. So we are lucky, weirdly, in that way, that it is edge on, or at least mostly edge on.
Yes, exactly. And my other comment would be to all the people that are doing the exoplanets, discovering the exoplanets. If those exoplanets were slightly off kilter from our observation, we wouldn't see them either.
Yes.
So how many exoplanets are we missing?
Yes. So I'm not an expert in that, but I had to do a little bit of it in grad school. It's using speckle imaging and stuff like that. It's quite good in finding exoplanets, and we target the types of stars that we think will have exoplanets around them. Like for example, you need time for that protoplanetary disk for things to kind of glomp together and make planets. If your time from cloud to star is only, say, 10,000 years, that's not a whole lot of time to make planets before the disk gets blown apart by the star waking up. So you don't expect there to be many planets around really big, bright O and B type stars. You expect them to be a dime a dozen around M dwarfs, which is what we mostly point our exoplanet telescopes at. And in those, we do sort of double up the combination of looking for the ones that are edge on through radial velocity surveys and looking for the ones that are plane on by doing the sort of like you try to cover up the star and see if you can see any other light. Yes, so that is an excellent point. And the people who do exoplanet studies spend a lot of time figuring out both the methods and the statistics for knowing how many they're missing, even despite the methods that they've developed.
But I had a very quick second question.
Yep.
Do you ever look at Betelgeuse naked eye and ponder over what's going on?
Yes. It's super easy to see because the Orion is so iconic, and it's nicely visible in the northern hemisphere in the winter. So yeah, when I look up at it sometimes, for a little bit I was like, you're getting on my nerves because this paper is like taking a really long time. But mostly I'm like, you have a buddy next to you, and that's fun.
Great.
Thank
Well,
you.
thank you very much. And thank you, Richard, for your questions. I'm not going to say, oh, and here's a gift for you. We now have two calendars. We have a local one that Jim Johnson has put together and the national one.
Lovely. Thank you so much.
You're welcome.
I look forward to this every year.
So you have stopped sharing.
Yep, I have stopped sharing.
I'm not gonna I'm gonna try not to jinx it this time.
Yeah. I think that was just my laptop being a bit curmudgeon-y.
Okay, Robert, did you want me to just go through this? Okay. Okay, so so I'm working with material that Robert put together and I sort of ended a bit. And so the normal Sky This Month PDF is great. Where's great? There you go. That it's up online now, right? So you can download that. And if you have this Night Sky Guide by Nicole Mortellero, I'd recommend that as well. So so this is stuff that I took from document. So Mercury is a morning object right now. We're going to see a picture of it in a minute. And Jupiter and Saturn. Jupiter is quite prominent right now. Easy to see. Saturn's setting, before midnight now, so we're almost getting past Saturn. And Uranus and Neptune are up there, also setting. When Uranus is up there all night, and Neptune is setting partway through. So a few of the observing highlights. December 19th, which is 2 days away, that's going to be a new moon. So I think tomorrow night might be clear. I don't know about December 19th. Yeah, close enough. Sure. 3i Atlas, it's going to be its closest approach to Earth, December 19th, but the magnitude's down to about 16.6. So it's tough ask for that. December 22nd and 23rd is the peak of the Ursids meteor shower, and December 27th is the first quarter moon. January 3rd is the peak of the quadrantids, and I'm going to say a little bit about that in a minute. The full moon is on January 3rd, and January 3rd is also when Jupiter is very close to the moon. So this is actually what the sky will look like on January 3rd at 10 o'clock and in close to Gemini. And January 10th, Jupiter's at opposition, so that's about as big as we're going to see it. And that's also the last quarter moon, so when the moon comes up at midnight. And so some of what the sky is going to look like, this is January 1st, which is sort of halfway to the next meeting. Orion, which we've just been hearing about, is pretty prominent now in the southern sky. And there's our friend. Have we said Betelgeuse 3 times already? And the Orion Nebula here, there's a beautiful image in Anna's talk, the Rosette Nebulas. Over here, the Christmas tree cluster. Jupiter is still going to be up there. The Pleiades and so if you head out from Orion, there's the Pleiades up here. You can see them if it's dark as sort of a fuzzy, but they're beautiful through any kind of optics. And the Hyades is an open cluster, sort of near Aldebaran. And Saturn's kind of exiting stage right. So that's looking north. Oh, that's looking south, and looking north. There's Polaris, the Elephant Trunk Nebula. We see that sometimes. And there's Cassiopeia, and you go up, there's Andromeda, and you sort of work your way along here and sort of using this star and this V of Cassiopeia as pointers, and find Andromeda in there, and Triangulum in here. We're going to see a picture from Robert in a minute of Triangulum. Another thing that's really nice to look at is the double cluster. And I've just put in the comets that are in principle visible, but these two are actually setting very early, and this one's just about done. So it's not like the Comet Festival we had a month or so ago. And here's the 2 meteor showers we mentioned. And of course, Gary was the star of the Geminids. He was on TV and on the radio. So, but the weather, yeah. The weather wasn't that great, but you saw some Geminids.
My camera actually picked up.
Yeah, so we'll see that coming up. And what about these ones?
They come with surprises.
Okay.
Sometimes they're boring, and then other times they just pop out.
Okay,
Sometimes
so
you just hit that mother load, and it's just fantastic.
Okey doke, so that's something. So now I'm actually gonna call on Gary, because he's volunteered to do the Crater of the Month.
Yes, the crater of the month. Seems like everybody's a deep sky observer these days, and they blame when the full moon is up or when the moon's up at all. They don't want to watch it at all. Well, I'm gonna tell you, tonight I'm gonna teach you one of the beautiful things of looking at the moon. I'm gonna talk about the crater of the month. Magnesius. Wow. How do I just press the button?
Yeah,
Okay,
or you use the little wheel.
the wheel. Okay, there we go. So it's in the highlands. Most people miss the highlands. The highlands are down here, and everybody misses Maginus because it's an old crater. They're all into the Tycho, which is the bright one, has the great big rays. But Mega, it's been around for 3 billion years. It's been beaten up. The walls are knocked down on it. It has just a geology fossil of Newfoundland. I should say the moon. Okay. Here's a close. Now, the best time to watch it is first quarter and last quarter. Full moon, you can't even see it. The full moon just takes everything away. You don't get to see the craterlets. You don't get to see it. But when it comes to first quarter, the shadows come in. Just look. You can actually just can you see the arrow in the crater? That's for the low angle. The sun breaks through the wall of the crater, which has been knocked down, and creates this nice arrow. It's called the arrow. It's really cool. Matter of fact, the last time we were up for the first moon lunar thing, up that place where I worked, Geo Center. I had a kid, 12 years old, looked through the thing and said, "What's that arrow down there, mister?" He picked it up. Okay, it has lots of heads. Now, once you find the arrow, everybody goes looking for the X, but you don't have to go all over the way for the other X. Pick the X here. The X, which is just another peak. But as the shadow comes in, this is so high up, the peak of it makes an X. So you don't have to go looking, just look in this one. You've already found an arrow. You found an X. And for those people who are pirates, can you see the skull? There's the eyes, there's the nose, there's the mouth. All in one beautiful thing. And it only happens when the shadow is great. And matter of fact, I was looking at a picture the other night where someone had 13, mouth dry out, 13-inch. And because we all know the moon wobbles, you get a different angle every now and then. And this angle that he had can actually have a nice view of the gap. Really? When you go up, look at the moon, take this in a start. That's it. Thank you.
And that's how you do Crater of the Month. So Gary, is this right at first quarter or?
Yeah, around first quarter, when the angle is, the sun haven't dropped water.
Okay,
Chris was mentioning there's another skull on top there. It looks like a skull man with a hat. You can see there.
If you look at the very top of the crater. Yeah, it's right,
Yeah,
yes, there it
that's
is.
what I was.
Okay.
Like a head with a hat.
Yeah.
okay.
That's just.
So right around first quarter though.
Yeah. That's all on the north side, so who cares?
Okay,
So when's the best time to look at that area?
First quarter and last quarter, when the sun angle is low, it is, and it changes so fast, it's kind of cool. Right, and you forget about it every now and then, because I said, Claudius and Tycho take everything else out. And now, when it's full, you can't see nothing.
okay, and I'm actually gonna point out Tycho and Copernicus, so now I'm embarrassed to do that, but they're okay too, but they're not as cool as this one, so. Anyway, so I don't know if Kim's joining us tonight, but So these are our solar images from the last month. So Kim started it off with the solar images just as this group of sunspots was starting to rotate onto the face of the sun. And this is just with her DSLR, and she used an eclipse filter from Celestron, but made for a DSLR. And then so that was the end of November. A few days later, so going left to right, I think this was 4296, 4294, and 4298. And so Randy got a nice shot of the sunspots and then zoomed in on them. And you can see the Sea Star really does a super job on solar images. And so this was December 2nd. I tried the same day with my hydrogen alpha. So my sunspots aren't quite as good, but I did get a prominence here. And then a few days later, December 6th, you see the sunspot group has moved across, but there were a lot of prominences that day. And with the solar filter, like the white light filter, like Kim's and Randy's, you can see the sunspots very well. You don't see the prominences. This kind of telescope, the PST and the center has one as well, and a few people have them. You can see the hydrogen, so you can only see one line of hydrogen, the hydrogen alpha line, and so you can see the prominences with that kind of telescope. You can't see that with the white light scope. So solar system objects. So here's the moon again, and that's Tycho and Copernicus. And this was one of the first shots I did with when I finally got all the bits and pieces so I could attach a flattener to my little telescope 61 EDPH3. And that's looking in close at Copernicus. That's Stadius. And there's Tycho. Tycho and Copernicus are rayed craters. That means they're much younger than Maginus.
Magnus in that shot?
Yes, it is.
Yep. Which one is it? Where?
Just down to the right, I think. Yeah.
Down there?
No.
Go over to the right underneath.
Right.
Right there.
That one.
Oh,
Okay.
Okay.
That's it.
It's quite Tycho.
Yeah. Okay, good. Yeah, good question. David Coffey did a nice shot of the moon. Kim did a shot in the snow. Yep. So that's December 5th. And then I, using things set up differently, this with an 80 millimeter refractor and a Barlow, took a shot, which also got Tycho, and I guess Maginus is down in there somewhere. And John Peddle did the nice thing, or the interesting thing here is he did two shots separated by almost 4 hours. And you can actually see, if you look up here, for example, things have moved just a little bit. And he would say, Gary, which C is this one? Yeah, right.
Crisis.
And you can, there you are, John Peddle's, he's online. So you can see the edge of it here, and then it's lost here. Do you want to say a little bit about that, John?
Yeah, it's just what you said. I just wanted to see how it would change over the space of a few hours. And if you overlap them and jump back and forth, you can see like there's a rotation there too. Allow with the shadow moving a little bit.
I'm just going to turn you up a little bit. Yeah, so you can, so say that again about the rotation.
Yeah, if you overlay the two of them and like skip
Oh.
back and forth between them, you could see like a rotation, like the Tycho was rotating a little bit.
Oh, yeah, you can, yeah. Very hard to do it with them separate.
Yeah, you can't do it side by side.
Yeah, anyways, that's an interesting thing to do. Thanks. And then Kim did another shot of the moon on December 7th. I did a shot of Jupiter December 6th, and Io is actually right on the edge there. I don't know if you can see it. You can't really see it up there. And there's the shadow of Io there. And Kim, now this is a really interesting shot. Kim did this just with her DSLR and 800mm lens. And there's Ganymede, and there's Europa, and there's actually two moons right there. You can see it looks a little bit extended. And when you look on Stellarium, that's in fact what's supposed to be there. Io and Callisto. So that was a really neat catch. And Tim and Sue, that's a lovely image. That's with a 9.25 inch telescope that does a nice job. And then this one, Kim got a shot December 7th of the moon and Jupiter. Can you see that on the screen?
Yeah, very dim.
Oh, yeah, it's there. Again with her DSLR. I tried Saturn, that's a little bit over sharpened, but not much. And Chris got Mercury. So that's the lighthouse over there. And there's Mercury right up there. And so
That's the backup photo. The expedition was to try and photograph Mercury's sodium tail.
yeah,
And yeah, it looks so calm and serene, but it was blowing the gale. I was cowering in the lead of my car. The monoplane camera with the sodium filter was in the rear of the car, but the wind kept blowing the cable out of the back, blowing the laptop off of the stool. And I gave up and my fingers were killing me, so I put.
So we
took up my iPhone, which is an old iPhone, it's not even good. And managed at least to get.
we should maybe have a little cheap medal for each meeting, the sort of persistence of the month or something like that. And that's probably getting pretty close to it. Okay, so this one's interesting. Is Bernard online? I don't think so. Okay, so we'll see what happens. This is 3I Atlas, which is the one that is not an alien spaceship, but it is an interstellar. And okay, so now I need to slide this over here. So Randy, is that going out on the Zoom?
Yeah.
Okay, so you can actually see it's moving. So he was catching this image over, I forget the amount of time. It was a couple hours, I think. And so that's pretty impressive. Yeah. Oh boy. And then he stacked his 240 30-second images. So that's 120 hours, or 120 minutes. Pretty impressive. And that's what it looks like. And it does look like a comet. And Randy got C2025K1 Atlas, and I think that must be just about gone now too. That is, so do you think that one was breaking up? Is that why the head looks like that?
Most of that is the movement, but it was so thin, the seas there couldn't catch the fragments.
Okay. And this is the meteor camera shot that Gary was mentioning. Okay, which ones are Geminids? Oh, which ones are monoserids?
They're the dimmest ones. There was only 4 on that one. Type of thing. They're all in that same little area where you're at.
So in there. Okay, and the other ones you think are Geminids?
Oh, I know are.
Okay. And this was just too pretty to leave out. This is a shot from Cape how do you say this? Anguille? Yep. And then I got a shot November 23rd, very young moon, and Cynthia got the same shot with her cell phone. And so getting deep sky, we didn't have much deep sky observing this this month, but Jim Johnson is starting another project. So this was the first one we saw. So this is there is the belt of, yeah, well, almost. There's the belt of Orion there. So Alnitak, El Noam, and Mintaka, Horsehead, the Flame Nebula. What's out here? Flaming Star. I forget what that is. And then he put that together with another shot of the that's got M42, the Orion Nebula. So he's in the process, I guess, next time we ever have a clear sky, he'll start filling this in, and eventually we'll have all of Orion. So this is something to look forward to from Jim. I was just trying out my new telescope and flattener, and it was cold, so I tried something easy, which was just an open cluster here near Lacerta, and there it is there, NGC 7243, and mostly I was just making sure that the flattener had gotten rid of some of the vignetting, which is sort of difference in brightness around the edges. We're still seeing a little bit from Cygnus. I had to try on part of the Veil Nebula, which is a supernova remnant in Cygnus. There's the East Veil, West Veil, Fleming's Triangle, and I tried the East Veil, but didn't. This was before I had the flattener. Didn't really frame it very well, but that was just trying to make things work. Randy did the Pleiades, which is an open cluster. So these are not very old stars that were formed together. They're going past some dust, but that is not the dust that they were made from. But it's a beautiful sight, even with, well, especially with binoculars. I think that's a beautiful sight. And Robert has a really nice shot of the Triangulum Galaxy. A lot of stuff going on there. So, what's that? 30 times 5 minutes. So it's a couple hours in that, and very nicely processed. Very nice star colors. Full calibration stuff. So very, very nice work there. And that's it. So just a reminder, next meeting, we're going to hear about the 60th anniversary. We're going to celebrate the 60th anniversary of the center, and Ezekiel's going to tell us about false color imaging. And so thank you to everybody online. For the people in the room, we have some wraps, some fruit, some sweets over there, some coffee, some pop. So we're going to have a little bit of a holiday celebration. And so thank you all for coming, and thank you for joining us online. Thank you. Okay, so for the folks online, thanks for joining us. I'm gonna shut that down now and start turning off the system. So bye, everyone. Bye, David.
Merry Christmas.